In the YouTube video titled Lecture 19, Elgamal Digital Signature by Christof Paar, Professor Paar presents a comprehensive analysis of digital signatures, building upon the previous week's discussion of RSA. He meticulously structures the lecture around 3 distinct chapters, delving into attacks against RSA, exploring the Elgamal signature scheme, and dissecting its inherent weaknesses. Professor Paar initiates the lecture by dissecting the RSA digital signature scheme, exposing a vulnerability known as existential forgery. This attack, executed by a malicious actor named Oscar, highlights the potential for generating a valid message signature pair without knowledge of Bob's private key. Oscar leverages the inherent simplicity of RSA, where the message is directly used as input for an exponentiation operation employing Bob's private key. Professor Paar subsequently transitions to a discourse on Elgamal digital signatures, a scheme that distinguishes itself by introducing the concept of ephemeral keys, temporary private keys generated for each individual message. He emphasizes the paramount importance of these ephemeral keys in safeguarding the scheme's integrity, underscoring that they must be uniquely generated for each message to ensure security. In the final chapter, Professor Paar delves into the vulnerabilities and attacks inherent to the Elgamal scheme. He cautions against the practice of reusing ephemeral keys, demonstrating how this lapse in security can lead to an existential forgery attack similar to the one presented in the context of RSA. Professor Paar convincingly articulates that while reusing ephemeral keys offers a seemingly advantageous efficiency boost, it introduces a significant security hazard, potentially enabling Oscar to compromise Bob's private key. Additionally, he presents another attack that grants Oscar the ability to forge a valid signature for a message without knowledge of Bob's private key. Professor Paar concludes the lecture by emphasizing the indispensable requirement of utilizing unique ephemeral keys for each message in the Elgamal scheme to thwart these aforementioned attacks. He aptly situates Elgamal as the cornerstone of the digital signature algorithm, DSA, a widely adopted and respected signature algorithm. From 0 minutes to 5 minutes of the video, Professor Christof Paar welcomes viewers to the second week of his lecture on digital signatures, a topic he introduces as exciting. He reminds the audience that the previous week's lecture covered security services and an introduction to RSA digital signatures. Today's lecture continues the discussion with the goal of delving into the foundational principles of digital signatures. Specifically, Professor Paar outlines 2 primary objectives: demonstrating a specific attack against RSA digital signature schemes and introducing the Elgamal digital signature scheme. From 5 minutes to 5 minutes of the video, Professor Paar delves into a compelling vulnerability in RSA digital signatures, aptly termed existential forgery. He elucidates how an adversary, designated as Oscar, can circumvent Bob's private key to generate a seemingly valid signature. Oscar's stratagem involves selecting a signature value, S, from the set of integers modulo n, where n is a substantial 2000-bit number. He then computes x as s raised to the power of the public exponent e modulo n. Subsequently, Oscar transmits x and s to Alice, deceptively claiming it to be a message authenticated by Bob. The crux of the attack lies in Alice's verification process. Alice, unaware of the forgery, raises s to the power of the private exponent d modulo n, obtaining x. Professor Paar highlights that this process invariably yields a valid signature, even though Oscar lacks knowledge of the private exponent. This unveils a significant security lapse. To mitigate this existential forgery, Professor Paar proposes a countermeasure involving the imposition of strict formatting rules on the message x. This rule mandates that the final 124 bits of x must be set to ones. He argues that this enforced structure hampers Oscar's ability to fabricate a valid signature as x becomes a random number, significantly reducing the probability of coinciding with the prescribed ones pattern. Following this discourse on RSA's limitations, Professor Paar introduces the Elgamal digital signature scheme, offering a contrasting approach. Elgamal operates within a discrete logarithm setting, utilizing different parameters. From 10 minutes to 15 minutes of the video, Christof Paar elucidates a method for mitigating the existential forgery attack on RSA digital signatures. This technique involves implementing formatting rules, effectively constraining the structure of the message undergoing signature. As an illustrative example, Paar proposes a restriction on the message payload to 900 bits, with the remaining bits padded using a pattern of 124 consecutive ones. This constraint significantly diminishes the attacker's capacity to generate valid signatures for arbitrary messages. Paar proceeds by introducing the little FMA theorem, a fundamental principle in modular arithmetic. This theorem posits that for any integer a and prime p, a caret p1 equals 1 mod p. The significance of this theorem lies in its implication that modular arithmetic computations with a prime modulus can be simplified by reducing the exponent modulo p1. Applying this theorem to the Elgamal signature verification process, Paar demonstrates the simplification of the verification condition. He highlights that the attacker's ability to control the outcome of the message being signed is limited by the inherent properties of the Elgamal signature scheme and the random nature of the ephemeral key. Paar emphasizes the crucial necessity of avoiding reuse of the ephemeral key, as such practice would render the private key vulnerable to compromise. He then introduces a second type of attack, again classified as an existential forgery attack. This particular attack strategy involves the attacker generating a valid signature for a predefined message. Paar showcases how the attacker can compute a signature that satisfies verification by leveraging the previously discussed formatting rules. Paar concludes by outlining the inherent limitations of this attack, emphasizing the attacker's inability to manipulate the message being signed. This restriction stems from the inherent randomness of the message, which is intrinsically determined by the signature scheme. Paar reiterates that although the attacker can generate signatures that validate, they lack the capacity to directly influence the content of the message itself. From 15 minutes to 20 minutes of the video, the speaker delves into the limitations of the existential forgery attack against RSA digital signatures. This attack hinges on a malicious actor, Oscar, generating a forged signature, S, and subsequently calculating a corresponding message, X, based on a publicly known exponent, E. The speaker elucidates that Oscar's inability to directly manipulate the semantic content of the message renders this attack less practical in real-world scenarios. To mitigate this vulnerability, a common practice is to implement stringent formatting rules on the message being signed. A straightforward example involves specifying a fixed message length of 900 bits, with the remaining 124 bits filled with ones. This formatting constraint presents a significant obstacle for Oscar, necessitating the brute force exploration of an astronomically large number of combinations, 2 to the power of 124, to discover a message conforming to the stipulated format. This computational burden renders the attack effectively infeasible. The speaker then introduces the concept of an ephemeral key, a temporary key generated and utilized exclusively for each message before being discarded. This emphasizes the paramount importance of ephemeral key uniqueness to safeguard the integrity of the signature scheme. Reusing the ephemeral key for multiple messages creates a substantial security breach, enabling malicious actors to forge signatures and compromise the system's trustworthiness. From 20 minutes to 25 minutes of the video, Professor Paar delves into the vulnerabilities inherent in the Elgamal digital signature scheme, departing from the idealized textbook presentation. He first scrutinizes the potential for existential forgery, a type of attack that allows an adversary to create a valid signature for an arbitrary message. Paar emphasizes that while the Elgamal scheme, like RSA, relies on the difficulty of the discrete logarithm problem, it is susceptible to attacks that exploit implementation details rather than fundamental cryptographic weaknesses. He illustrates this by demonstrating an attack that hinges on the reuse of the ephemeral key. This temporary key, generated for each signature, is designed to be unique to ensure security. However, an adversary observing 2 signatures generated using the same ephemeral key can exploit this repetition to deduce the signer's long-term private key. Paar presents a solution: strict adherence to the principle of ephemeral key uniqueness. Each signature must be generated using a distinct temporary key. This, while increasing computational overhead, effectively mitigates the vulnerability. He then briefly addresses a practical consideration: the bit length of Elgamal signatures. Due to their structure, these signatures can be significantly larger than the message being signed, potentially imposing a burden on bandwidth-constrained applications like contactless payments. Paar concludes this portion of the lecture by noting that despite not being as widely utilized as RSA, the Elgamal scheme serves as a foundational element in other widely employed signature schemes like DSA, digital signature algorithm. From 25 minutes to 30 minutes of the video, Professor Paar delves into the concept of formatting rules as a countermeasure against existential forgery attacks in RSA digital signatures. He highlights that, rather than accepting any arbitrary 248-bit number as a message, RSA mandates a specific format. This format stipulates that the message's payload, or actual content, be restricted to 900 bits, followed by 124 ones in the least significant bits. This deliberate imposition of structure on the message mitigates the possibility of Oscar generating a valid signature for a message with a predetermined content. Professor Paar then elaborates on the formidable computational burden associated with this attack. He explains that Oscar would need to execute an average of 2 to the power of 124 trials to forge a signature with a message containing 124 trailing ones. This astronomical number of attempts underscores the infeasibility of such an attack, making it an impractical strategy in practice. Moving on to Elgamal Digital Signatures, the professor emphasizes the criticality of employing unique ephemeral keys for each message. He demonstrates that if Bob were to reuse the same ephemeral key for two distinct messages, X1 and X2, Oscar could exploit this vulnerability to deduce Bob's private key, D. Professor Paar provides a compelling illustration of this by showcasing how Oscar could derive an equation for D using the available information: S1, X1, R, and K. This highlights the paramount importance of utilizing a distinct ephemeral key for every message to safeguard against such a breach of privacy. From 30 minutes to 35 minutes of the video, the speaker delves into the criticality of avoiding key reuse within the Elgamal digital signature scheme. He elucidates that while such a practice might seem computationally advantageous, it inadvertently introduces significant vulnerabilities. The speaker employs a hypothetical scenario involving Bob, Alice, and Oscar to demonstrate the potential for an attacker, Oscar, to exploit a reused key. The core of the attack hinges on Oscar's ability to surreptitiously acquire the private key, D, by leveraging the repeated use of the ephemeral key, K. The speaker elaborates that Oscar, having gained control of the private key, can manipulate the message, X, and produce a valid signature. This effectively empowers Oscar to forge a message that appears authentic to Alice. The speaker underscores the inherent weakness of this attack. While Oscar lacks the capability to generate a message of his specific choosing, he can create a valid signature for any arbitrary message, essentially forging it. To illustrate this vulnerability, the speaker provides a concrete example using a 248-bit prime number for the discrete logarithm problem. In this instance, the resulting signature length would be a considerable 4,096 bits. Consequently, a valid signature could be generated for any message of that size, even if it is not a message that Oscar intended. The speaker concludes by emphasizing the paramount principle. When employing Elgamal digital signatures, one must always utilize a fresh ephemeral key for each distinct message. This practice guarantees the message-specific nature of the signature and effectively thwarts potential forgery attempts by an attacker. The speaker further asserts that this principle extends beyond Elgamal signatures and holds significant weight for other cryptographic schemes as well. From 35 minutes to 40 minutes of the video, Christof Paar delves into the verification process of Elgamal digital signatures. He commences by outlining the verification procedure, involving the calculation of an auxiliary parameter denoted as T. This parameter is derived by raising beta to the power of R and subsequently multiplying it by R raised to the power of S, all taken modulo P. Paar then underscores the critical role of the little FMA theorem, which postulates that for modular arithmetic operations with a prime modulus p, any base raised to the power of p1 invariably yields a result of 1. This theorem serves as a foundational principle for simplifying the verification equation. He substitutes beta with its equivalent representation, alpha, raised to the power of d, and similarly replaces R with alpha, raised to the power of k. Paar meticulously guides viewers through an algebraic simplification process, showcasing how certain terms cancel out, ultimately leading to a concise expression. Alpha raised to the power of I times S modulo P. The congruence of this final expression with the original construction of the message X, which was determined as S multiplied by I modulo P1, substantiates the accuracy of the verification process. Paar concludes this segment by emphasizing the correctness of the verification procedure, thereby confirming the robustness of Elgamal's signature scheme in this particular scenario. From 40 minutes to 45 minutes of the video, the speaker delves into a critical vulnerability within the Elgamal digital signature scheme, demonstrating how a malicious actor, represented by Oscar, can exploit this weakness. Oscar's objective is to forge a valid signature for a message, ideally one that would enable him to illicitly transfer funds from Bob's account. To achieve this, Oscar strategically selects integers I and j with the constraint that their greatest common divisor, GCD, with P1, must equal 1. He then calculates a signature composed of two components, R and S, based on these chosen integers. This signature, along with the target message, is transmitted to Alice for verification. Alice, relying on the established protocol, computes a value T using modular arithmetic, which involves raising beta, Bob's public key, to the power of R, the first part of the signature, and multiplying it by R raised to the power of S. The result is then taken modulo P. A valid signature is confirmed if T is congruent to alpha, the generator of the cyclic group, raised to the power of X, the message modulo P. The speaker emphasizes that when performing operations on exponents within modular arithmetic, particularly with a prime modulus P, the modulo operation can be applied directly to the exponent. He demonstrates this by representing the exponent m as a multiple of P1 plus a remainder R. This insightful application of the Fermat's-Little theorem allows the speaker to simplify the verification equation and expose a crucial vulnerability. The crux of the attack lies in Oscar's ability to generate a valid signature without complete control over the message content. This echoes the concept of an existential forgery attack seen previously with RSA. Oscar can effectively create a valid signature pair, but the message itself is essentially random. The speaker clarifies that the Elgamal digital signature scheme, as presented in this basic form, is susceptible to this specific vulnerability. This underscores the importance of meticulous design and implementation of cryptographic systems to avoid predictable weaknesses. From 45 minutes to 50 minutes of the video, Professor Paar delves into the vulnerabilities inherent in the Elgamal digital signature scheme. He emphasizes that the reuse of ephemeral keys constitutes a significant security lapse, urging viewers to avoid this practice. To illustrate this point, he presents a scenario in which Bob, the signer, employs the same ephemeral key for two distinct messages, labeled X1 and X2. Professor Paar then elucidates how Oscar, the adversary, can exploit this shared ephemeral key to breach Bob's private key. Oscar, by observing the signature parameters, R and S, associated with both messages, constructs a system of equations containing two unknowns, X1 and X2. Solving this system, Oscar can effectively determine the ephemeral key, thereby exposing Bob's private key. Professor Paar underscores that possession of Bob's private key empowers Oscar to forge authentic-looking signatures on messages of his choosing, effectively impersonating Bob. An example he provides involves a message instructing a bank to transfer 1,000 euros to Oscar's account. If Oscar could sign this message with Bob's private key, he could potentially execute a fraudulent transaction. The professor concludes this segment by stressing the gravity of this vulnerability, emphasizing that a unique ephemeral key should be generated for every message signed. He also hints that there will be homework assignments designed to reinforce this crucial security principle. From 50 minutes to 55 minutes of the video, the speaker delves into the critical aspect of key management within Elgamal digital signatures, specifically the ramifications of key reuse. He asserts that employing a unique ephemeral key for each message is paramount to maintaining the integrity of the signature scheme. To illustrate this principle, he presents a hypothetical scenario where Bob, inadvertently or deliberately, reuses a temporary key for two distinct messages, denoted as X1 and X2. While superficially innocuous, This practice introduces a significant vulnerability that an adversary, represented by Oscar, can exploit. The speaker elucidates that Oscar, in possession of the public keys and the compromised ephemeral key, can effectively deduce Bob's private key. The crux of Oscar's attack lies in the simultaneous use of the information gleaned from both messages to solve a system of equations. These equations express the relationship between the signature components, S1, S2, messages, X1, X2, and the private key, D. S1 equals X1, D asterisk R asterisk, inverse of K. S2 equals X2, D asterisk R asterisk, inverse of K. Through algebraic manipulation, Oscar can eliminate the shared term D asterisk R asterisk, inverse of K, resulting in an expression that isolates D, thereby revealing Bob's private key. This compromise fundamentally undermines the security of Bob's digital signature scheme, as Oscar gains the ability to forge signatures for any desired message. The speaker concludes by strongly advocating against the reuse of ephemeral keys, emphasizing the importance of adhering to this principle to ensure the secure operation of Elgamal digital signatures. He underscores the critical nature of this concept by alluding to its relevance in future academic exercises. From 55 minutes to 60 minutes of the video, the speaker delves into the potential vulnerabilities of the Elgamal digital signature scheme. He cautions against the practice of key reuse, demonstrating the precariousness of employing the same ephemeral key for multiple messages. To illuminate this vulnerability, he presents a scenario where Bob, unwittingly, utilizes the same ephemeral key to sign two distinct messages. Oscar, the adversary, astutely observes that both signatures share a common R value while exhibiting different S values. By exploiting this pattern, Oscar can effectively solve a system of equations, thereby uncovering Bob's private key. This compromised private key then empowers Oscar to forge authentic signatures for arbitrary messages, effectively subverting Bob's signing authority. The speaker underscores the paramount importance of avoiding key reuse, advocating for the generation of a unique ephemeral key for each digital signature to mitigate this critical security flaw. From 60 minutes to 65 minutes of the video, the speaker delves into the vulnerabilities of the Elgamal digital signature scheme, focusing on the potential for existential forgery attacks. They emphasize that while a direct manipulation of the message's semantic content is not feasible for Oscar, the adversary, they can still generate valid signatures with a chosen signature attack. This method leverages the public exponent E and the modulus N to compute a message X from a chosen signature S, according to the formula X equals S to the power of E mod N. This parallels the existential forgery attack previously demonstrated for the RSA algorithm. The speaker then introduces a common countermeasure to mitigate such vulnerabilities: the implementation of formatting rules. They propose a straightforward illustration involving a 248-bit message X, where the actual message M is restricted to 900 bits, and the remaining 124 bits are filled with ones. This formatting rule significantly hinders Oscar's ability to generate valid signatures, resulting in a vanishingly small probability of success, 1/124, making the attack practically infeasible. The core of the speaker's analysis lies in the vulnerability associated with the ephemeral key K, used in the Elgamal scheme. Oscar can exploit the reuse of this temporary key K for two distinct messages, X1 and X2, to compromise Bob's private key D. By observing the signatures R, S1, and R, S2, generated for X1 and X2, respectively, Oscar can solve for D, using the equations S1 equals X1, D asterisk R mod P, 1, and S2 equals X2, D asterisk R mod P1. In conclusion, the speaker highlights the inherent susceptibility of the Elgamal digital signature scheme to existential forgery attacks, even when formatting rules are in place. The speaker emphasizes that Oscar can still generate valid signatures by randomly choosing a value for K, and employing the formulas R equals alpha caret K mod P and S equals M D asterisk R asterisk J to the power of -1 mod P1, where M represents the message, J is a randomly chosen integer, and alpha and beta are the public key parameters. This underscores the necessity for robust security measures to ensure the integrity and authenticity of digitally signed information within the Elgamal framework. From 65 minutes to 70 minutes of the video, Christof Paar delves into the significance of formatting rules in RSA digital signature schemes, underscoring their efficacy in mitigating existential forgery attacks. He elucidates that the standard RSA protocol employs a 248-bit message, granting the attacker latitude to select any 248-bit value. To enhance the scheme's robustness, a formatting rule is introduced, dictating that the message be padded with 124 ones at the end, augmenting the message length to 900 bits. Paar then proceeds to calculate the probability of an attacker successfully guessing the correct bit pattern, demonstrating that it equates to 1/2 124, or roughly 2 to the power of 124 trials on average. This computational burden, Paar stresses, effectively renders the attack impractical and serves as a potent countermeasure. Paar then elaborates on the inherent limitations of this attack, emphasizing that the attacker lacks control over the semantic content of the forged message. This implies that the generated message may be devoid of real-world significance, rendering the attack more of a theoretical concern. Despite this theoretical nature, Paar cautions that the attack constitutes a cryptographic weakness, as it demonstrates the system's vulnerability. Paar concludes his analysis by asserting that RSA schemes in practical applications employ far more intricate mechanisms to thwart such attacks. From 70 minutes to 75 minutes of the video, Professor Paar elucidates a vulnerability inherent in the Elgamal digital signature scheme, enabling an adversary, Oscar, to forge signatures without possessing Bob's private key. This vulnerability stems from the scheme's reliance on ephemeral keys, which are generated anew for each signature. Oscar exploits this by strategically selecting integers I, J, and Y, ensuring that the greatest common divisor of J and P1, where P represents the large prime number defining the finite field, is 1. He then constructs a signature pair RS by computing R as alpha raised to the power of I times beta raised to the power of J modulo P, and S as the negation of R multiplied by the modular inverse of J modulo P1. Professor Paar demonstrates the validity of Oscar's forged signature through a rigorous mathematical proof. He substitutes the expressions for R and S into the verification equation utilized by Alice, the intended recipient of the signature, and, through a series of algebraic manipulations, applies Fermat's Little theorem to demonstrate that the verification process yields a true statement, effectively validating the forged signature. This underscores the critical flaw in the Elgamal scheme, allowing Oscar to generate arbitrary messages coupled with valid signatures without needing to compromise Bob's private key. From 75 minutes to 80 minutes of the video, Professor Paar delves into the Elgamal digital signature scheme, highlighting a prevalent attack vector that compromises its integrity. He elucidates that an adversary can forge a seemingly legitimate message signature pair without possessing the requisite private key. This constitutes a significant vulnerability, as it undermines the core principle of secure authentication. The professor meticulously dissects the attack mechanism, illustrating how the assailant can calculate the signature using publicly accessible information and a randomly generated number K. To mitigate this vulnerability, Professor Paar introduces the concept of formatting rules. He posits that imposing stringent formatting requirements on the message, such as mandating a 900-bit payload followed by 124 consecutive ones, effectively hinders the attacker's ability to generate a valid signature with ease. This is due to the vanishingly small probability of the attacker randomly generating the requisite bit pattern for the signature, which equates to a 1 in 2 to the power of 124 chance of success. By employing this simple but effective countermeasure, the susceptibility to existential forgery attacks against RSA digital signatures can be significantly reduced. From 80 minutes to 82 minutes of the video, Christof Paar delves into the vulnerabilities inherent in the Elgamal digital signature scheme, particularly highlighting a scenario where an attacker could exploit the reuse of ephemeral keys. Paar posits a scenario where Bob, the signer, mistakenly employs the same ephemeral key, K, to sign two distinct messages, denoted as X1 and X2. This lapse in security grants Oscar, the adversary, the ability to surreptitiously derive Bob's private key, D, by exploiting the relationship between the signatures, S1 and S2, generated for X1 and X2, respectively. Oscar accomplishes this by calculating the difference between S1 and S2, multiplying this value by the shared ephemeral key K, and finally dividing the entire expression by R, a parameter common to both signatures. This calculation yields the private key D, effectively granting Oscar the power to forge signatures for any message. Paar underscores the criticality of this attack, emphasizing that it empowers Oscar to masquerade as Bob, granting him unfettered control over the message content and signing process. This highlights the paramount importance of employing unique ephemeral keys for each message, thereby preempting such vulnerabilities and ensuring the integrity of the digital signature system.